Welcome, welcome all of you to the 12th lecture of Digital Electronics. In this lecture, we will be dealing with AND gate and OR gate. So coming to AND gate. Okay. So what is an AND gate? We are having a gate which is having some input, say two inputs. I am considering two inputs A and B, and one output X. So the logic of AND gate is the input will be high. Will be high only if all the inputs are high. So if you are writing the truth table of an AND gate, how will it be? A and B are the inputs, H is the output. So these are the inputs and this is the output. If A and B is high, output is high. If A and B is low, then the output is low. Low, high, low. Again, high, low, low. Okay. Now, if you are representing it using logic 0 and logic 1, you are having inputs, output A, B, X. 1, 1, 1. 1, 0, 0. 0, 1, 0. 0, 0, 0. Okay. So this is the basic truth table. This is the truth table of a AND gate. Okay. So how to represent an AND gate using a symbolic form? In symbolic form, it is written in the form of like this. In D. So you are having inputs A, B, and the output is X. So the AND operation is basically given by dot. So you can write H is equal to A dot B. Okay. So this here I have mentioned about two input NAND gate. Sorry, two input AND gate. Now coming to three input AND gate. So this is two input AND gate. Now next one is coming into three input AND gate. Okay. So here the AND gate will be having three inputs A, B, and C. The output is X. So if I am drawing the truth table of that, how will it be? Having inputs, outputs. A, B, C, and X. So here you can write. See here the input is 3 bit. Therefore we can write, if you are converting 3 bit into decimal, you can count from 0 to 7. So write the corresponding binaries of 0 to 7. So 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, and 7. See what is basically 3 input AND gate? It is H is equal to A dot B dot C. So here what happens? If A, B, and C is high, then only output is high. So and how? That is 0. Here we get 0, 0, 0, 0, 0, 0, and the last one is 1. Okay. So this is basically a 3 input AND gate. Now coming into a basic diode logic. So diode logic or DL of two input AND gate. Okay. So I am having a plus 5 volt supply. Two diodes are there, A, B. Okay. So here I am having a resistor of value R. Okay. I am connecting here. Okay. I am connecting and taking output at this point with respect to a ground. Okay. So this is V0. Now, if A is 0 volt and B is 0 volt. So here what happens? A is 0 and B is 0. So this acts as ground. So this acts as ground. Therefore, the output voltage will be 0 volt. Okay. Now, if my value is A is equal to 1 volt, A is equal to 0 volt and B is equal to 1 volt. In that case also what happens? This is 0 volt. So the current passes directly here. That means the output is also 0 volt. Output appearing is 0 volt. Okay. So that is regarding when A is equal to 0 volt and B is equal to say 1 volt. Now, okay. Now when B is equal to 1 volt, what happens is that there will be a reverse biasing of this diode D2. So what happens is that the current will not pass through this one, but the current I passes through R and R diode 1 and A, and the resultant output voltage will be equal to 0. Next one. Next case. Next case I am keeping A is equal to 1 volt and B is also equal to 0 volt. So what happens? The current will pass through this part, this area. Now, so D1, D2. A is equal to 1 volt. Since the diode biasing voltage is 0.7 volt, 1 volt, so what happens is that, or okay, so instead of here I am keeping 5. Okay, so it is easy to understand. So what happens here also? Here is 5, here is you will get 5. So there will be no voltage across these 2 points, so that current will not pass through D1. Again, B is 0 volt. So what happens? The current will directly pass through here. So what happens is that the output voltage V0 becomes 0 volt, because there is a path of current. Now, next case. Next case is I am keeping A as 5 volt as well as B as 5 volt. So A is 5 volt, B is also 5 volt. In this case what happens? These two diodes D1 and D2 will get reverse biased. D1 and D2 will get reverse biased. So therefore the only path of the current is in this track. So in that case what happens? You will get the output voltage as 5 volt. That is, when you are getting the output voltage, when both the inputs are there, when both the inputs are 5 volt, you are getting the output voltage. So this is basically the diode logic. That means if you are drawing it in this pattern, say input, output. Okay. So A, B, say V0. If A is okay, I will start with the least one. If A is 0 volt and B is 0 volt, output is 0 volt. And if A is 0 volt and B is 1 volt, again the output is 0 volt. If A is 1 volt and B is 0 volt, the output is again 0 volt. 1 or 5. Okay. Now, when A is 5 volt and B is 5 volt, then the output is 5 volt. Hope you have understood the concept of diode logic. So this is the basic diode logic of a 2-input AND gate. Now next one I am going to explain about the logic of 2-input AND gate. 2-input AND gate, resistor transistor logic. Resistor transistor logic. Okay. So first of all, let me draw two switches. Means I am taking two transistors. Say T1, T2. Two transistors as input. Then here I am connecting A to the base of the transistor 2. I am connecting B. Okay. So here I am having a resistor R. Then another transistor is there. Another transistor. These two are grounded. So this is T3. So I am taking output voltage X. That is again with respect to ground. So that is V0. Here I am supplying plus 5 volt as VCC. Again these two are shorted. So in this case what happens? When A is 5 volt, when say I am supplying a 5 volt here, when A is 5 volt and so we start from 0 volt and then it will be easy. Okay. When A is 0 volt and B is 0 volt, what happens? There is no gate pulse if A is equal to 0 and B is equal to 0 volt. There is no base for T1 and T2. That means T1 and T2 is not on. That is T1. One connection I have here. That is T1 and T2 is not on. If T1 and T2 is not on, then T3 is not on. So what happens? You will get output voltage is 0 volt. Okay. When gate of T1, that means if base of T1 and T2 is not on, then T3 is also not on. So you will get V0 as 0 volt. Okay. Now next one is, if I am having okay, so I think you have now next one. I think I have erased that. Okay, so I will once more draw it. The resistor transistor logic, RTL. Resistor transistor logic of AND gate. Okay. We are having input A and B. A and B are connected as base of two transistors. These two are interconnected. This is connected to another transistor. So this is T1, T2, T3. Okay. So here we are having a resistor. Here we are having another resistor. Here we are supplying plus 5 volt. Resistor R, AB, and here we are connecting it to ground. And the output I am taking from here. Okay. Now here what happens? 0 volt I have explained. When A and B is 0 volt, okay, what happens? So I will write it as a truth table in the case of transistor biasing. Okay. Shall go with first one, T1, T2. Okay, and A and B I am writing it towards downside. Okay, now when A is 0 volt and B is 0 volt, what happened? Transistor 1 is not on and transistor 2 is not on. That means so here I am getting the output. Okay, this is the input. Okay, so what happens? So T3. So what happens? Since the output of T1 and T2 is not there, T3 is also not on and the output is so. Now again, if AB is 0, 1, that means A is 0 volt and B is 5 volt. So here what happens? Transistor 2 is on, but transistor 1 is not on. That means you are not having the path. You are not having the path from path here. So what happens? If that path is not there, here what happens? Only transistor 2 is on and transistor 3. Some bias, it will get on, and if it is getting on, so what happens? Another path is also there. So what happens? The output voltage will become so. T3 is on. Okay. Again, if it is 1 0, again the same thing will happen. 1 0 1 0. Again, if both are on, T1 and T2 will be on, and T3 will be on. Okay, and T3 will be on, which produces an output voltage of 5 volt. That means 1. Okay, so I think you have got the concept of resistor transistor logic of an AND gate. Okay. Now coming into next one is OR gate. In OR gate I will try to explain only the resistor transistor logic. Yeah, I will try to explain a resistor transistor logic and not resistor, diode logic. I will try to explain the digital logic. Then you will be able to understand the diode logic. That is all. No, digital diode logic. Okay. Now next gate is what? Next gate is OR gate. OR gate. In OR gate, here the basic logic of OR gate is if I am considering if any one of the input of OR gate is logic high, then output is logic high. Okay. That means if you are writing the truth table of a 2-input OR gate, I am having A and B as inputs, A and B as inputs, and X as output. Okay. 0 0, you will get 0 0 1 1 1 0 1 1 1 1. That means at least one of the input should be logic 1. Okay. So if I am drawing the OR gate, we can draw like this. Okay. So this is A, this is B, and this is X. Similarly, if you are having a 3-input, okay. Similarly, if you are having a 3-input OR gate, how will it be? Let us A, B, and C. A, B, C. Here you will get inputs. Output is X. So you can write from 0 to 7 in decimal form or in binary form. 0 0 0 0 0 1 2 3 4. That is 1 0 0 5 6, and last one is 7. So this is 0 1 1 1 1 1 1 1. So if you are drawing a 3-input OR gate, you can draw like this. So having A, B, and C. Here is you are having is X. That means if any one of the input of OR gate is logic high, then output is logic high. So if you are having a two input NAND gate, two input OR gate, then it is represented by H is equal to A or B. So addition symbol or plus symbol is used here as OR. If it is three input, we can write it as H is equal to A or B or C. Okay. Now coming into the diode logic of this OR gate. Coming into the diode logic of OR gate. So I will explain the two input. Okay. So here I am having A. A is connected to a diode. Diode is D1. B is connected to D2. And here we are having a resistor R is grounded. Okay. Here we are having the output X. This is also grounded. So we will get V0. Okay. Now see the what D1 will conduct if supply is greater than 0.7 volt. So I am giving the supply as say I am giving 0 volt, 0 volt. If both are 0, what happens? The output is 0. Since if A and B are 0 volt each, then the output X is also 0. Okay. Now, when A is made high, when A is equal to say 5 volt and B is equal to 0 volt, what happens? The supply goes like this. So what happens? You will get output voltage as 1. Okay, you will get our logic high. Output voltage you will get it as 5 volt. That means if A is 5 and 5 volt and B is 0 volt, then output is 5 volt. Similar is the case with B. If B is 5 volt and A is 0 volt, then output is 5 volt. Again, if both are 5 volt, then also you will get the output as it will not get added up. Since this is parallel, it will not get added up. So what happens is that if 5 volt and 5 volt input is there, you will get output as 5 volt. This is the basic diode logic or DL of two input OR gate. Okay. Next one is I will explain about the resistor transistor logic of OR gate. Resistor transistor logic RTL. This resistor transistor logic of OR gate. Okay. So I am having I'm going for two input OR gate. I am having A and B as input. So A is given to the transistor T1. B is given to another transistor, that is B is given to transistor T2. This is the resistor here. This is given to T2. Now here I am having a supply of plus 5 volt. Standard here. Then another resistor R. I am connecting it to T3. I am connecting it to T1. T2 and T3. This is grounded, and this T2 is connected. So these four are connected to the base of T3. Okay. So here I am getting the output. So I am getting the output V naught of H. So here what happens? When A is 0 volt and B is 0 volt, what happens? T1 and T2 is not on. If T1 and T2 is not on, then the output, say V01. V01 is the output of T1 and V02 is the output of T2. V01 is the output of T1 and V02 is the output of T2. If A and B are 0 volt, if A and B are 0 volt, then V01 and V02 is equal to 0 volt, which means that the gate of T3 is not triggered. Which means output V0 is equal to 0 volt. Remember that T1 and T2 are in off condition. Again, if A and B are 5 volt, if A and B are 5 volt, then T1 is on. That means V01 and V02 have some voltage. Say I am having 5 volt, and that 5 volt is the say I am having say some volt, say H volt, and what happens is that the output will be high because T3 become conducting, and you will get the output voltage as high. That means output of T3 is triggered, and V0 is equal to 5 volt. Similarly, okay, if A and B. Now, if A or B, if any one of them is 5 volt, if A or B, any one of them is 5 volt, okay, that means either V1 of n, V0 of 1 will be high or V02 will be high. In both these cases, output T3 is triggered. And this 5 volt appears in V0. V0 is equal to 5 volt. Okay. So that is basically the resistor transistor logic of OR gate, of 2-input OR gate. Okay. So in this lecture, what I have done is we have studied about logic gates. We have studied about AND gate and OR gate. So we have dealt with what is a gate as initially as a black box, then defined what is an AND gate and give the symbol for AND gate. And if it is a 3-input, okay, the symbol for AND gate is dot. So we will get H is equal to A dot B. Now for 3-input AND gate, it is equal to H is equal to A dot B dot C. Okay. Now I have explained about the diode logic of 2-input AND gate. Okay. So I have given the different conditions of input. A is equal to B is equal to 0 volt, A is equal to 0 volt, B is equal to 5 volt. A is equal to 5 volt and B is equal to 0 volt, and A is equal to 5 volt and B is equal to 5 volt. So here the condition is if both the inputs are high, then only output is high. Now I have also explained the resistor transistor logic. This also the case is the same, but only difference is you are using transistors. Here transistors act as switches. Then we have dealt with OR gate. What is an OR gate? That is the basic symbol of OR. That is A OR. Okay, plus or addition stands for OR, and the basic truth table of OR. And a diode logic of 2-input OR gate and resistor transistor logic of 2-input OR gate. So that is all in this lecture. In the next lecture, we will be dealing with NOT gate. We will be dealing with NOT gate and introduction to a NOT gate and XOR gate. We will be dealing with NOT gate as well as XOR gate, and after that we will start with universal gates. Thank you.